Hello, welcome back. Today we will learn about second order derivatives. So second order derivatives means we have to differentiate a given function two times. Okay, so for example, if there is a y which is a function of x, and if I have to differentiate this first, then we will differentiate both sides with respect to x, that is d dx of y will be equal to d dx of f of x. Okay, so and let us write d dx of fx as f dash of x. Okay, so this is dy over dx. Now in second order derivatives we will differentiate again this equation both sides with respect to x. So let us differentiate both sides with respect to x. That means we have to differentiate dy over dx with respect to x, and here also it will become d dx of f dash of x. Okay, so now d dx of dy over dx should be written as d2y by dx2. So this is the symbol of second order derivative, and this will be equal to d dx of f dash x. We will write f double dash x. So here in a way, this, if we see that f with double dash of x, then it means that this function has been differentiated two times. Okay, so this is the symbol of second order derivative, that is d2y by dx2, or you can also see f double dash of x. Okay, so there are other ways to write also, like if y equals to f of x, and if I differentiate both sides with respect to x, then y can be written as y1 also. Okay, and this will be equal to d dx of fx is f dash of x. Now again, if I differentiate both sides with respect to x, then here we will write y2, and d dx of f dash x is f double dash of x. So it's simply you have to differentiate the given function two times. It's just as simple as that. So we will look some questions, and you will be much more clearer. So here the question is asking to find the value of d2y over dx2 if y equals to log of x. So first here it's y equals to log of x. Now if I differentiate both sides with respect to x, then here it will be dy over dx equals to d dx of log x is 1 over x. Now again we will differentiate both sides with respect to x, then it will be d dx of dy over dx equals to d dx of 1 by x. Now this can be written as d2y by dx2 equals to, now here d dx of 1 by x is d dx of this 1 by x can be written as x to the power minus 1, and using the formula it will be minus 1 x to the power minus 1 minus 1, and that is minus x to the power minus 2, and hence it can be written as minus 1 by x square. Okay, so the value of d2y by dx2 is minus 1 over x square. So here one thing I want you to note, that treat this portion as formula, that is d dx of 1 by x is directly you can write minus 1 by x square. Question number 2, prove that d2y by dx2 is equal to dy over dx whole square if e to the power y x plus 1 equals to 1. So here first let us write the given equation, that is e to the power y x plus 1 equals to 1. Okay, so here let us differentiate both sides with respect to x at first. So here it will be d dx of e to the power y into x plus 1 equals to d dx of 1, and here we will be using rule because first function is e to the power y into x plus 1. So let us keep e to the power y here and differentiate x plus 1 plus keeping x plus 1 at first and differentiating e to the power y equals to d dx of 1 is 0. So this implies e to the power y into, say d dx of x is 1 and d dx of 1 is 0. So 1 plus 0 will be simply 1 plus x plus 1. See d dx of x, e to the power y. So here if you notice that there is e to the power y, not x. Okay, so for the time being we will consider this y as x, then d dx of e to the power x will be e to the power x only. So here first it will be e to the power y only, but we have to differentiate y also using chain rule. So this will be equal to 0, and this implies e to the power y plus e to the power y into x plus 1 into dy over dx equals to 0. So here let us take out e to the power y common, then 1 plus x plus 1 dy over dx equals to 0. Now since exponential function cannot be 0, so I can take this e to the power y to the left hand side, so it will be 0. That means 1 plus x plus 1 dy over dx equals to 0, and hence x plus 1 dy over dx equals to minus 1. Therefore dy over dx will be equal to minus 1 by x plus 1. Now since we have got the value of dy over dx, now we will again differentiate in order to get d2y by dx2. So differentiating both sides with respect to x again, then it will be ddx of dy over dx equals to minus ddx of 1 by x plus 1. So this is d2y over dx2 equals to minus, now here if you remember in just previous question I have told you that ddx of 1 by x is 1 by x whole square. So for a while I will consider this everything as x. So this is ddx of 1 by x, and the derivative of it is minus 1 by x square. But using chain rule I have to differentiate x plus 1 also. Hence d2y by dx2 equals to minus minus will get plus, so it will be 1 by x plus 1 whole square, and this portion if you notice it is simply 1 only, because ddx of x is 1 and ddx of 1 is 0, so 1 plus 0 is 1. Hence my d2y by dx2 equals to 1 over x plus 1 whole square. Now the question was asking to prove that the value of d2y by dx2 is same as the value of dy over dx whole square. Now since I've got the value of d2y over dx2, that is 1 by x plus 1 whole square, now I will simply square this portion both sides. So if I square this portion both sides, then I'll have, if I square this both sides, then I will get dy over dx whole square equals to, see, minus square is positive and 1 square is simply 1, and denominator there is x plus 1 and it will be x plus 1 whole square. So if I compare, then I see that dy by dx is also coming 1 by x plus 1 whole square, and the value of d2y by dx2 is also 1 by x plus 1 whole square. That means it is proved. Question number 3, if x equals to a times theta plus sine theta, that is x is a function of theta and y is also a function of theta, then we have to find the value of d2y by dx2 at theta equals to pi by 2. So first we will differentiate the given equations of x and y with respect to theta, because both are the functions of theta. So here if I differentiate both sides with respect to theta, then we will get dx over d theta equals to a is constant. See, dd theta of theta is 1 plus dd theta of sine theta is cos theta. So dx over d theta is a into 1 plus cos theta. And if I differentiate y with respect to theta, then here it will be dy over d theta equals to a into, now see, dd theta of 1 is obviously 0, here there is minus, and dd theta of cos theta is minus sine theta. So the value of dy over d theta equals to a sine theta. Therefore dy over dx can be written as dy over d theta divided by dx over d theta, and putting the values, a sine theta divided by dx by d theta is a into 1 plus cos theta. So here a and a got cancelled, hence the value of dy over dx equals to sine theta by 1 plus cos theta. So from here ddx of dy over dx equals to ddx of sin theta by 1 plus cos theta. So this becomes d2y by dx2 equals to, now here it's very important to notice that this theta inside, that is, this is the function of theta and we are differentiating with respect to x. Okay, so first we will treat everything as x and at last we will differentiate theta with respect to x. Then using the quotient rule, I will have 1 plus cos theta, first denominator, into ddx of sin theta minus, keeping numerator and differentiating the denominator, that is 1 plus cos theta whole divided by denominator square, that is 1 plus cos theta whole square. So this will be equal to 1 plus cos theta ddx of sin theta. See here we are differentiating theta with respect to x. So first we will consider this as x, then ddx of sin theta will be first cos theta, but since it was not the function of x, so we have to differentiate theta also. So we will get d theta by dx minus sin theta, ddx of 1 is 0 and ddx of cos theta would be minus sin theta, but again we have to differentiate theta also with respect to x, whole divided by 1 plus cos theta whole square. So here it will be cos theta into 1 plus cos theta into, now what to do with this d theta over dx means, here as you see that we have dx over d theta as a into 1 plus cos theta, then d theta by dx can be written as 1 by a into 1 plus cos theta. So similarly here minus minus will get plus sin square theta into d theta by dx can be written as 1 by a into 1 plus cos theta whole divided by 1 plus cos theta whole square. So this will be equal to, we can cancel here 1 plus cos theta and 1 plus cos theta, but let me keep for a while as it is. Here in numerator we will have a into 1 plus cos theta as LCM, and in numerator we will have cos theta into 1 plus cos theta plus sin square theta whole divided by 1 plus cos theta whole square. So it will be, so let us open the bracket there also, then here there will be cos theta into 1 is cos theta plus cos theta into cos theta is cos square theta plus sin square theta whole divided by a into 1 plus cos theta, and if I put the inverse of that, then here it will be 1 by 1 plus cos theta whole square. So here if you notice, then I can see that cos square theta plus sin square theta is 1. So here we can write cos theta plus 1 in numerator, and in denominator we have a 1 plus cos theta into 1 plus cos theta whole square. So we can cancel this 1 plus cos theta and 1 plus cos theta, hence I will get the value of d2y by dx2 as 1 by a into 1 plus cos theta whole square. Now since we had got the value of d2y by dx2, the question was asking to find its value when the value of theta is pi over 2. So here we will just put the value of theta as pi by 2, that is the value of d2y by dx2 when theta equals to pi by 2 will be equal to 1 by a into 1 plus cos pi by 2 whole square. So it will be equal to 1 by a and 1 plus cos pi by 2 is 0, so it will be 0 whole square, and hence my answer will be 1 by a only. Question number 4. If y equals to a cos nx plus b sin nx, then we have to prove that d2y over dx2 plus n square y equals to 0. See here, y is a function of x. Here a, b and n are just numbers. So let us differentiate both sides with respect to x. Then we will have d dx of y equals to d dx of, see a is constant, so it will be d dx of cos nx plus b is constant, d dx of sin nx. So this implies dy over dx equals to a, see d dx of cos nx is minus n sin nx. So this is by chain rule, you can do step by step, plus b is constant and d dx of sin nx is n cos of nx. So let us take out minus n common here, so we will get a sin nx minus b cos nx, since we are taking out minus common. Now let us again differentiate both sides with respect to x. Then we will have d dx of dy over dx equals to minus n a into d dx of sin nx minus b into d dx of cos nx. So this implies d2y by dx2 equals to minus n, and again differentiating sin of nx, we will get n cos of nx minus b. d dx of cos of nx is minus n, so that minus and minus, this minus will get plus n sin of nx. Now let us take out n common again, then that n and this n which is outside already will become n square, and inside we will have a cos of nx plus b sin of nx. And if I look at the question and notice that a cos of nx plus b sin of nx can be written as y, so that value is coming here. So instead of this I will simply write y, then d2y by dx2 will be equal to minus n square into y. Now let us bring everything on the left hand side, then it will be plus n square y equals to 0, and hence this was the equation which the question was asking to prove here. Question number 5, here y equals to x to the power x, then we have to prove that d2y over dx2 minus 1 by y into dy over dx whole square minus y by x should be equal to 0. So before differentiating the given function, let us operate both sides with logarithm. As you can see, there is function and in the power there is another function. So operating both sides with logarithm, then we will get log of y equals to log of x to the power x. So this implies log of y equals to x log of x. Now let us differentiate both sides with respect to x, then we will have d dx of log of y equals to d dx of x into log of x. So this implies d dx of log y will be 1 by y and dy over dx equals to, using product rule, we will keep x first and differentiate log x, and d dx of log x is 1 by x, plus keeping log x first and differentiating x, we will get 1. Hence 1 by y dy over dx equals to, here x and x got cancelled, then we will simply get 1 plus log of x. That means the value of dy over dx will be equal to y into 1 plus log of x. Now in order to get the value of d2y over dx2, let us again differentiate both sides with respect to x, then we will have d dx of dy by dx equals to d dx of y into 1 plus log of x. This implies d2y over dx2 equals to, let us use the product rule again, then keeping y at first and differentiating 1 plus log x, we will get d dx of 1 is 0 plus d dx of log x is 1 by x, plus keeping 1 plus log x first and differentiating y, we will get dy over dx. So that means d2y over dx2 will be equal to y by x plus 1 plus log of x into dy over dx is there, and since we have got the value of dy over dx as y into 1 plus log x, so we will put the value here. So it will be into y into 1 plus log of x. So the value of d2y over dx2 is y over x plus y into 1 plus log of x whole square. Now let us write the left hand side of the given equation, that is d2y over dx2 minus 1 by y into dy over dx whole square minus y by x. So writing my left hand side, then we have d2y by dx2 minus 1 by y dy over dx whole square minus y by x. Now we will put the values and we will prove that it is 0. Now let us put the value of d2y over dx2 from this particular equation, that is dy over dx2 is y by x plus y into 1 plus log of x square. Let us put it here. So it will be y by x plus y into 1 plus log of x whole square. After that there is minus 1 by y, so minus 1 by y, and there's dy over dx whole square, but we know the value of dy over dx is y into 1 plus log of x from this equation. So it will be y into 1 plus log of x whole square, and this minus y by x. Now as you can see that this y by x is positive and this y by x is negative, so they already become 0. And here it will be y into 1 plus log of x whole square minus 1 by y into y square into 1 plus log of x whole square. And if you see, there's this y and the square is getting cancelled, so we will have y into 1 plus log of x whole square minus y into 1 plus log of x whole square. Therefore this term and this term will also get cancelled as they are same but the signs are different, and hence my final answer is 0, and this 0 is on the right hand side of the equation. That means we have proved the given equation. So with this video, this is the end of this topic as well as of this particular unit, that is continuity and differentiability. We have finished. So in next playlist or our next chapter would be application of derivatives. See, we have learned about differentiation in this entire playlist. So what will be the application of these derivatives, we will do in that another unit, or you can say another chapter. If you got some value from this videos, or if you got to learn some new things, and then please like this video and subscribe this channel, and just share with your friends also. Thank you and keep practicing. Bye bye.